The interlocking circuits here, engineers work from the same circuit, from the same control circuit for the disconnector air switch. All the interlocking circuits operate from the same interlocking circuits, yes, from the control circuit of the DS and the ES. So we notice here that it is written for you that your loop or your DC is used in the DS and ES control or interlocking. What is an interlocking circuit exactly? You might say, oh God, so now I'm going to control the interlock even for the breaker through this circuit. I would tell you, no, the breaker's interlock is found within the control circuit of the breaker itself, right or wrong? When we were explaining here, the closing circuit of the breaker itself had all the interlocking conditions specific or set to the circuit breaker. However, in the case of the disconnector air switch, its interlocking must have its circuit stored from the same DC that is specific to its control. Okay, I will find myself going to page 9A, which is this page, all right? Then from this page, I will go to page 11 and so on until I reach page 13, which is the interlock page. So if you look here, you will find it written as interlock condition circle, all right? Interlock condition circle. Now, let's take a look at my circuit here. The first thing I will find is that it shows me the positive and negative from below here, all right? And here I have the auxiliary relay or the contactor, which is called key 1. Before it, I have the emergency position, which is a selector switch for the emergency position. And here I have a push button or a switch, you could call it, which is a self-return key. It's the type of switch where you turn it on, and if you release it, it will self-return or go back to its normal position again. All right, great. This circuit or this part is related to something we call interlock bypassing. What does interlock bypassing mean? It means you might have interlock circuits that are indeed complete, but you have some issue. For example, in the electrical circuit. So of course, if the electrical circuit is not complete, it won't allow you to execute a close or open command for any command you have. Therefore, if you are sure that the interlock circuit is indeed fulfilled, for example, you are sure that this is a closed name, or whatever you saw physically or with your own eyes and are certain of it, you can do something called interlock bypass. This will overlook any circuit related to interlocking and will immediately allow the closing or opening of any command you want. Okay, that's not what I'm going to focus on. I'm just going to focus on the interlock specific to each rate. Okay, I brought this here for us to talk about it now. Let me tell you that I want to close the disconnector switch, which is D627. All right, the disconnector switch D627. All right, the D627, okay? To close this disconnector, what are the conditions that must be verified, which need to be fulfilled so I can close the disconnector switch? I'll drive the disconnector switch. Let's see together. We said now that the disconnector switch is something that opens and closes without load, because if it opens and closes on a load, it means that electrical current will pass through it. That's why we even said it is used for you to choose if you want to connect your circuit breaker to it only. Whether the power is imported or exported, meaning whether you're taking power from the bus bar and giving it to the line, or the power is coming from the line and you are giving it to the bus bar. The other thing we mentioned is that as a result of this scheme being used or in size, meaning it is inside a tube within gas, of course, you cannot handle it. You will install a breaker. Since it is inside a tube within gas, of course, which means you cannot handle it. As a person, you cannot do a rack in or rack out, meaning the breaker is not withdrawable. You will install a breaker and the breaker will be fixed. Okay, that's why I want to isolate the breaker from the bus side and the line side so I can integrate it into the system. That was the second purpose of using the disconnector switch. Beautiful articulation, beautiful. Okay, so now I'm completely sure with you that I cannot open this disconnector or operate it under load. Can you explain this a bit more so that I, as an electrician, can understand you better instead of feeling like it's just a general story? I'll tell you. Okay, the point is that the disconnector should not be opened or closed under load, meaning there must be no voltage difference between the terminals of the disconnector. What does it mean to have no voltage difference? It means the voltage before the disconnector and after the disconnector must be synchronized. You might say, great, I can do like a circuit breaker, check synchronization and close the disconnector. I'll tell you that's wrong. Why? If the bus side is live and the line side is dead and you close it, if the bus side is live and the line side is dead and you close the disconnector, what will happen? Focus with me. Let's say this circuit has voltage, the voltage is shown in red and it's energized. Now let's assume the breaker was closed and the disconnector is closed, all of it is closed, and you went to the point of love. Let's say this is closed. Let's not make the red color part. It means I'm ready. I'm telling you that here in this part, everything below is closed. Consider that you didn't have all these interlocks and it was possible to operate the disconnector. Now, if this part below is indeed all closed and there are loads present, there's still no electricity. Let's assume this has 115 kilovolts. Here it is rotating. Kilovolt. Okay, is it live? All right, and this other side is essentially a load, meaning you're just flirting with the load. So the quality here is 0. Great. If you close this disconnector, will an arc be generated at the terminals or not? Of course, it will be generated. Why? Because it's a closed circuit. You're closing a circuit, so current will flow, creating an arc at the terminals of what? At the terminals of the disconnector switch. This is if this side is live, and this side is dead. Now, suppose both sides have a voltage of 132 kilovolts. All right, but are you sure? Sorry, 115, my apologies. Both had 115 kilovolts. Are you sure that both are exactly 115 kilovolts? Are you sure the phase shift between them is 0? Are you sure the frequency difference between them is 0? Of course not. You might say, just do a synchro check. Do a synchro check, do a synchro check. Oh, close the breaker, close the disconnector. The disconnector takes about 3 to 4 seconds to close. During those 3-4 seconds, the 2 points will definitely drift apart again with the term synchro check. You are checking the voltages until they match, then you close the breaker. The breaker closes in milliseconds, so it catches the 2 points together, whereas the disconnector takes 3 seconds, during which the 2 points might drift apart again. Consequently, at the moment of closing, you might experience a spark or arc. You want to ensure, my friend, that when I close the disconnector, one side has a supply and the other side must be dead. You might say, well, I just told you this is a load. And I told you that here all of this was dead. This is a load. I would say, no, load doesn't mean dead. Load means 0 voltage. But if you close the disconnector in a complete circuit now, by God's grace, you will be closing it and an arc will be generated. What do you want? I want a dead float, something called floating. What does floating mean, engineer? It means it's just hanging in the air. It's not a complete circuit, of course. You want one side to have voltage and the other side to be floating. Beautiful, engineer, very nice. So is it necessary for one side to have voltage? No, the important thing is that one of the sides must be floating, meaning it shouldn't have any voltage at all. Is this good? Good. Okay, let's think together. Okay, now I have a law. Rashad told me in a law yesterday or the day before yesterday, what is our law that she who looks at or considers the, and at the same time, I have the earth switch, which also looks at the disconnector switch, while the disconnector switch is the one that looks at the circuit breaker, and it also looks at the earth switch. Meanwhile, the earth switch looks at the disconnector, and the circuit breaker looks at the disconnector. This is the law I told you about yesterday. Now, let's think. First, let's assume that everything is drawn as it is in front of you. Normally, all the equipment or everything you were dealing with is drawn to be open. All right, let's say now I want to operate, to perform a correct operation. Okay, the first thing to do to close D627 is to look at the breaker and look at the earth. Good, good. First, let's talk about the earth. The earth is very easy. All the earth connections to its right, left, above, or below must be open. This way, I ensure that the breaker won't look at the earth, so the disconnector must look at what? At the earth. So that later, if I close the breaker, it won't result in a short circuit. Am I right? Yes, so which earth connection should be handled first? Like this, right? Go to the left, place it in the hole, there's nothing, the bus is done. Go to the right and you'll find here an earth Kisto 200 and Kisto 209. So you must ensure that Kisto 209 is open, not just ensure, you must ensure it is open. You must, not you have, you must ensure it is open. Clear? Good. Now go down here and you'll find Kisto 203. It must be open. Then go down here and you'll find Kisto 203. It must be open. Oh my. Okay, I'll go along with you. All right, good. So why are you looking here? Wait, look at me. Aren't you like this? Okay, the grounds are open and you look at the breaker. the breaker must be open. So when the breaker is open, why did you look at the ground here? It's done, the breaker being open, it makes a difference to you. What difference does the ground make to you? It doesn't make any difference. Your words are correct, of course, I can't say anything to you. However, among the rules of the GIS, we do not consider the breaker as an isolation point. So regarding the breaker being open or closed, I have nothing to do with it. But if you go down, why didn't you look at the ground, which is case 635, because that disconnector is open. Since this disconnector is open, it is considered an isolation point for you. So you have nothing to do with it. Is that clear, guys? Very good. So now you have looked at the ground, case 699, case 631, case 633. What about the three of them? The three of them, what about them? They are open, good. And what about the breaker? It's open. Now you have ensured that the grounds are open and you have ensured that the breaker itself is open. Why? Because you are worried if the breaker was closed. You close it so that it takes effort on him. Voltage might pass through you and it might go and affect other loads, right? I told you, right? So you ensure the breaker is open. Then you ensure that the area from the beginning of this breaker to that disconnect switch, this area is now settled. Right or wrong, the circuit is no longer closed on the load. It remained in the load. You reassured me, my friend. Really? No, I didn't reassure you. I tricked you. Why? What's the status of this other area? It's possible that this disconnect switch is actually closed. So when you came to close here, it's as if you're connecting electricity from this bus to that bus, like a bus section or a bus coupler, right or wrong? Oh, right, you're correct. So here, I also need to make sure that this disconnect switch is open as well. This way, I am completely assured that I am floating, that I am in the floating condition. So the first thing is that all the grounds are open. That's 1, 2, 3, because I don't consider it. And to ensure that this is floating or that one of its ends is in the air, not connected inside, the one next to it must be open and the breaker below it must be open. So this area in the bus is entirely what? This is the first thing to confirm regarding this 627. 627. All right, great or beautiful. You told me it's beautiful. Okay, let me tell you. Suppose this is how we suppose. All right, great. In front of solutions. So we made sure of everything and everything is fine. Okay, I came and told you what? I told you, suppose with me, I'm telling you, oh, suppose with me that this disconnector is closed and this breaker is closed and this disconnector is closed and you were feeding this transformer and this transformer was actually working. And for some reason, you now want to take out the bus that is underneath, you want to take it out for maintenance, or there is a problem with this bus or something. And what do you want to do? You want to transfer your load to the upper one. Is there a question? D630, don't worry about that. D630, Engineer Ehab, last time, good job. Engineer Ehab also asked a good question last time when we were all talking. Engineer Ehab, my point was, why is this separated like that? Here's the circuit breaker, here's the DS, here's the DS. Engineer Ehab, last time I confirmed that this ground is open, I confirmed that this ground is open, and I confirmed that this ground is open. As long as this breaker is open, and this breaker, sorry, here it is. This breaker is open, right? And this disconnector switch is open, so I don't care if this one is closed or not. This disconnector has nothing to do with that disconnector. You might ask me, why check this one? Check this one, because if it was closed, it would cause this disconnector and its closure to create coupling between the bus bars. But if this one is closed, it doesn't matter to me at all, even if this one is closed. Isn't the breaker here already open? It's not a problem, it doesn't matter to me, it won't affect anything. Okay, the condition I'm talking about now is a different condition. What is it? It's that the feeder is actually energized, meaning this is closed, as I mentioned, and the breaker here is closed, and this disconnector is closed, and this transformer is now energized and supplying a set of loads below. What do I want to do now? I want to take this bus out for maintenance. So, to take this bus out for maintenance, it's very simple. I can open the breaker, open the disconnectors, close the new disconnector, and continue with my work. But what do I want to do? I want to perform something called load transfer. Transferring loads from this bus to the other bus without affecting the load. Remember when we talked about choosing so that you can do, so that you maintain the system and you perform, there should be easy maintenance for different equipment and you minimize the outage. During maintenance time, right or wrong? So we finished the same talk. I want my feeder as it is, to transfer it from this bus to that bus while it is closed without cutting the supply to my load. Okay, great. How do I do that? He told you it's very simple. Now, if you close this disconnector, initially you need to check a set of grounds, right? What are they? This ground, and this ground. You might say they are already open, but I'll tell you, sorry, it's the law. We set a law, and unfortunately, with its advantages and disadvantages, you will have to check them anyway. Okay, great. You check them? Oh, okay, fine. You are reassured that they are open. Well, inevitably, you have to make sure of that electrically. I want to close this now. This side has a supply, and the upper side has a supply. Closing both together will work through what? Through my disconnector. So what's the solution? The solution is that I need to check the synchronization between the two. Now, if I check the synchronization between the two and then close the disconnector during the 3 seconds it takes for the disconnector to move, what could happen? Slipping, which is a difference. All right, between this wave and that wave of the voltages, a difference will be generated. So I want to make sure that these two voltages are typically the same. Both are typically the same. Let me tell you more clearly. I want these two voltages to be the same thing. No, I want these two voltages to be the exact same voltage, but from one source. I want to make these two the same thing. Keep in mind, I don't want them to be equal. I want them to be the same thing. Where is that? Okay, what should I do?